Hey, good morning. So first of all, the exams, I'm gonna bring the exams on Wednesday. So I almost done with the grading process. So you will get feedback on Wednesday. Second thing is we're gonna start a new topic today. On the second part of the semester, we cover the solution strategies for problems in general. Problems, linear programming models using the simplex method. And we learn how to solve those problems by hand using the simplex tableau. And also we learn how to solve problems using the computer, specifically using Excel and also using Ample. So today we're gonna continue our discussion now that we know how to solve problems. The next thing is to learn how to do some additional analysis with those solutions. So if you remember from Excel, once we solved the problems, there was an option there to run a sensitivity analysis from the solution that you obtained from the system. So we're going to explain that today. We're going to learn what the sensitivity analysis is representing, and also how it can be useful in terms of making decisions. So that will be today's lecture. We're gonna look into performing sensitivity analysis, what I call by hand, meaning that using solutions that you're solving by yourself. And then we're also gonna learn how to build this sensitivity analysis report using the computer. So here are the course objectives. This is what we set up to learn for this semester. And so far, this has been our map. So we learn linear algebra, we review concepts on linear algebra, and then we go through the introduction to linear programming model formulation. We learn how to solve problems using the graphical method. From there, we study different type of linear programming models that are more practical in the sense of representing more practical problems. These were problems that have more than 2 decision variables. So we talk about the production planning, resource scheduling, oil refinery, and so on. And then from there, we learn how to solve these problems using the simplex algorithm, in which we notice the importance of learning linear algebra and understanding the Gauss-Jordan method. And then we also apply the computer or use the computer to solve these problems. So far, these are the topics that we have, or the course objectives that we have covered. So today we're going to transition into the fourth one, which is interpret the model solutions and infer solutions to the real world problems. So learning objectives for this lecture discuss how changes in linear programming parameters affect the optimal solution. That's what we call the sensitivity analysis. So now, as I mentioned, when we were building these computer models, that we wanted to have the data separated from the model, because we want to see how these parameters that are provided for the model can impact our solution. So if you want to just change the parameter and see what impact that has in the solution, that's basically what the sensitivity analysis is doing. We want to see how the parameters or which bounds are satisfying certain limits for our optimal solution. Also, if we change the parameter, what impacts is going to have that in our solution, and so on. So we're also going to explain how to use the Excel solver output to answer questions of managerial interest, such as what is the most money a company will be willing to pay for an extra hour of labor? So that question is more in the sense of, are you going to be still making money if you increase your salary, the salary of your employees for $1? Or if you increase by $2 per hour, would that be profitable for you? So those are the type of questions that we want to answer. So the agenda for today, we're going to start with the graphical sensitivity analysis. Basically, we're going to follow the same process. If you remember with linear programming models, when we started solving them, we started with the graphical method, and then we transition to the simplex method. So we're gonna start with the basics. I want you to understand what's going on when we say, okay, I'm gonna increase this much, the right-hand side of the constraint. I want you to see what that means from a graphical point of view. And same thing with the objective function. If I change parameters in the objective function, I want you to understand what's happening from a graphical perspective. After that, then you will understand the algebra, because you have an understanding of what's going on in terms of a graphical perspective. Now you can apply the concepts to larger problems. So that's the strategy we're going to follow. We start with the graphical sensitivity analysis, and then we transition to the algebraic sensitivity analysis. And finally, we go into the computer. So again, these are our first weeks of the semester. We'll say 6 to 10 weeks. We look at modeling LP, solving two variable LP graphically, simplex method with the artificial solution. Subject matter of this section is in the LP, the parameters or the input data of the model can change within certain limits without causing any changes in the optimum. So this lecture explained the basic ideas of sensitivity analysis. So let's start with the graphical sensitivity analysis. And what this section is going to do is to demonstrate the general idea of sensitivity analysis using the graphical methods. So two cases will be considered. Again, we're going to look at the parameter, changing the parameters on the right-hand side of the constraints. And we're also going to study what's going to happen if we change the parameters of the coefficients of the objective function. So sensitivity of the optimal solutions to changes in unit profit or unit cost. Okay, so remember when we look at the or when we have a linear programming model, we have three parts: the decision variables, the objective function, and the constraints. So when I say I'm going to look at the right-hand side of the constraints, I'm focusing on the right-hand side, obviously, of the constraint, meaning that I'm going to increase or decrease the values of that area of the constraint, which often represents the amount of resources that you have available. So if you increase the amount of resources that you have available, or you decrease the amount of resources that you have available, how is that going to impact our optimal solution? And then optimal solution to changes in the unit profit of cost. What that means is in the objective function, I have a coefficient representing a cost or a profit. So I want to know what's going to happen if I increase or decrease that value. Is that going to change my solution? If it's changing my solution, by how much? And what does that mean in terms of making decisions? Okay, so we're going to start with an example from a manufacturing facility with two jobs or two products on two machines. So here's the job code manufacturing. Again, we have to keep it small in order for representing this graphically. So we're going to have only two products on two machines. A unit of product one requires 2 hours on machine one and 1 hour on machine two. For product two, one unit requires 1 hour on machine one and 3 hours on machine two. And we also have the revenues per unit cost for product one and two. Those are $30 and $20 respectively. And then the daily processing time available for each machine is 8 hours. So the formulation for this problem, we're going to have a decision to make. Actually, a couple of decisions. So our decisions are going to be our XI, which are the units of product I. Okay, so how many units of each product you're gonna produce? In this case, we have only two. The objective function is I want to maximize that profit, which is 30 for X1 and 20 for X2. And we have two constraints. For machine one, we know we have 8 hours and we know the requirements a unit for product 1 and 2 hours on machine 1, 1 hour on machine 2. For product 2, 1 unit requires 1 hour on machine 1 and 3 hours on machine 2. So my constraints are in terms of each machine. So we have 2x1 plus x2 less than or equal to 8. And this is for machine 1. And I have x1 plus 3x2 also less than or equal to 8 because we have 8 hours for machine 2. This is machine 2. And then my decisions have to be greater or equal to 0. So if we solve this problem graphically, you can see that picture on the right-hand side of your slide. We have a constraint for machine 1, which is this constraint right here. And then we have the constraint for machine 2, which is this one. And then the feasible region is limited by x1 greater or equal to 0, x2 greater or equal to 0. So we have that feasible region in that shaded color. And then if we use the isoprofit line, as we have explained before, we're going to find that the isoprofit line will look like this, something like this. So if we move that line, we're going to find that this is going to be the optimal solution. So we know how to proceed in order to get that value. Okay, so so far that's what we know. For the graphical method, we can identify the optimal solution, and that optimal solution for this problem is 3.2 for x1 and 1.6 for x2, with a profit of $128. But now we want to take this analysis a little bit further. So the new graph, so now we want to see what will be the impact of increasing, for example, the capacity of one of my machines from 8 hours to 10 hours. How is that going to change my solution? So for the first case, that's what we call the changes in the right-hand side of the problem. For the first case, the new graph illustrates a change in the optimal solution when changes are made in the capacity of machine 1. If the daily capacity is increased from 8 hours to 9 hours, the new optimum will move to point G. So what basically is happening now is you're changing the right-hand side of that first machine or that first constraint from 8 to 9. So that's going to move that constraint to the right of the plot, if you can see it in the figure. So now what's going to make difference now is the feasible region is going to be also changed. The feasible region is changing as you move that constraint to the right by increasing the capacity from 8 to 9. So what that means is that this area is also becoming part of the feasible region now. And that's just by increasing that unit of hours that you have for machine 1 in terms of capacity, you're increasing that by 1 unit. So that's moving that constraint towards the right. And that's also making a change in terms of your feasible region. So now your optimal solution is no longer located in C, because if you move that, we show this is the isoprofit line. If you keep moving now, your feasible region is gonna also include this area. So the optimal solution now is gonna be moved to this point. Okay, so if the daily capacity is increased from 8 to 9 hours, the new optimum will move also to the location of where those two constraints intersect in this case. So that will be this point. Okay, so you can observe how things are changing by just making a small change in the problem formulation. By just increasing 1 unit on your resource capacity, you are changing the feasible region, and also the optimal solution of the problem can change. So the rate of change in optimal resulting from changing machine 1 capacity from 8 hours to 9 hours can be computed as follows. Okay, so this is how we're going to compute the rate of change. That would be, in this case, the objective function value of G minus the objective function value of point C divided by the capacity change. So in this case, the objective function value, as we can observe here, for the problem in which we have 9 hours for machine 1 is 142. And the objective function value, you see that increased from 128 to 142. And the capacity change in this case is 9 minus 8. So what this means is that for every hour that I increase for machine 1, I'm increasing my profit by $14 an hour. Okay, so that's what this is telling you. If you increase 1 hour of machine 1, you're increasing your profit by $14. So that's the rate of revenue change resulting from increasing machine 1 capacity by 1 hour. So the question that you need tonight to ask yourself from a management point of view is, how much does it cost you to increase that extra hour? And you know that you're gonna make $14 more, but if it costs you $20 to increase that extra hour, then you're not making any profit. You're actually increasing your cost. But if increasing that extra hour is just costing you $5, then you want to go for that, right? Because you're going to be increasing your profit by $9 an hour. Okay, so that's the type of questions that we want to answer with this analysis. Okay, so we're just getting started. You're looking at the right-hand side. This example is showing you that if you increase the capacity for one of the machines by 1 hour, you have a rate of change or a rate of revenue change resulting from increasing machine 1 capacity by 1 hour of $14 an hour. Yes.
In real world, we find that our profit will increase by a little bit. Is there like any rules or anything based on?
So that's what I'm saying. Like, this is just telling you in terms of revenue.
Yeah, no,
but you need to understand
including all the you pay salaries, everything is like that profit will increase, like, let's say a little bit. Is there a reason you will accept that?
Okay, so I guess the question is, how much of an increase will make you make a decision, right?
Maybe you will not go for that.
If it is small. Okay, yeah, so that's a good question. So the question is there's a threshold in which you will say, okay, this is good enough for me to go in that direction, right, or not? That's a very good point, and I think it's gonna depend on the size of the company. Like if you're just, for example, you have a small company and you can see that $14 an hour can make an impact on your business. You want to try that, or you want to go for something like that. But if you're a multi-million company, $14 an hour, it depends on how many employers you have or how many machines you have. If it is just one machine that is just increasing $14 an hour, you might not go for that. But if you have 100 machines in which you can implement something like this, then that will translate it in more money. So that's a very good question, and the answer is there's no specific threshold. I think it will be more in terms of what type of environment you're working on, and if it's and you will understand management when you're working on your company. Either they will have their own, I will say, policies or protocols, like they want to see if they want to increase, or if they want to make a specific change, there will be certain goals that you will have to meet, not only in terms of cost and profit, but also like space that is going to be allocated for those changes and so on. So it will be more tied to the culture, I will say, within the company that you're working on. But that's a good question. Yes.
So if you change the capacity for both machines at the same time,
Yes.
would the capacity change still be one?
So that's a good question. So what will happen is this constraint, now we're looking at just one of the constraints, right? So this constraint will move up, and we'll have to look at what will be the value of that new objective function.
I guess my question is like, so like, it's still the same amount of time.
For
One of the machines that isn't running in this scenario.
Oh.
Last hour, so like you change both of them to 9.
yes,
Would the capacity change go to 2 or would it stay at 1?
so the question is, if you increase both by 9 by 1 unit, you make them both 9 hours. And yes, for that we're gonna have to solve and see what's gonna happen. But by just making machine 1 increase by 1 hour, you can see that maybe you can accommodate more product into your system. And that's because if we go back to the requirements for both products, you see that both of them requires more time for machine 1, right? If you see the constraints here, the ratio for the machines used, they both probably require more time for machine 1. So that's why by just increasing that machine, you're allowing that machine to run for a longer period of time, you will be able to accommodate more product. So from a practical point of view, basically what we're saying is, if you're going to run 100 units, then you will have some time. If you only want to produce 100 units with the current requirement, you will have machine 2 idle for some time. So by increasing the capacity of machine 1 only, you're basically allowing more product to run by machine 2 because of the time requirement. That makes sense? So
I'm trying to see on the graph, let's say if we both the output will change too much.
it will not change. Yeah, because if you look at the constraints, right, you see that X1 is associated with product 1, right? So so what I'm trying to say is, you see that product 1 requires more time than product 2, right? So by allowing machine 1 to run for a longer period of time, you're basically, let's go back here. Those are very good questions. So
No, I mean, it's not just
yeah, so actually, if you see the requirements for machine 1, there are not a lot of difference between them. So machine 1 requires for product 1 2 hours of machine 1 and 1 hour of machine 2. But then if you go to the second product, this one is requiring 3 hours on machine 2. So I guess if we increase the capacity of machine 2, both of them simultaneously, you should see an increase in the profit, but it might not be as high as $14. So let's see if we have that case in the next slide. Yeah, those are good questions. I don't have the numbers with me unless have that discussed later on. Let's see. So let's continue the discussion and we can come back to this to address that question. So the name of the unit work of a resource in a description of the rate of change of the objective function per unit change of a resource. So again, that unit word of a resource is a description of the rate of change of the objective function per unit change of the resource. Early LP developments have coined that abstract name the dual or the shadow price. So, and we will go back to the dual in our next lecture, but what we're trying to say is that understanding that number will help us make decisions, and there's a name for that number. Okay, so that number is called the dual or the shadow price. This name is now standard in all the LP literature and software packages. So if we go to the reports that are generated by Excel or by Ample, you'll see that there's, when they show this revenue change resulting from adding a capacity, that number is going to be named the shadow price or the dual price. Okay, so that's the name that is given to that rate of change. By looking at the graph, we can see that the dual price of $14 an hour remains valid for changes increase or decrease in machine one capacity that move its constraint parallel to itself to a point on the line segment B and F. So that's not going to change. That rate of change will remain the same as long as you are moving that constraint parallel to it within this line. So essentially what I'm trying to say is the following: as long as that constraint is, you continue to move that constraint within that segment, the rate of change is not changing. It's going to stay $14 an hour. Or if you move it back to point B. The name unit word, again, this is the same slide. By looking at the graph, we have seen that already. So we can compute machine one capacities at point B and F as follows. Let's see how that those numbers change. So I'm looking at the minimum machine one capacity at B. This is 0.0 to 0.67. If I substitute that into the constraint for machine one, which is 2x1 plus x2, that's going to be equal to 2 times 0 plus 1 times 2.67. That's going to be 2.67 hours. And the maximum machine one capacity at F equals 8 and 0. That'll be 2 times 8 plus 1 times 0. And that will be 16 hours. So the conclusion is that the dual price of $14 an hour remains valid in this range, 2.67 hours less than or equal to machine one capacity, less than or equal to 16 hours. So as long as we are changing the capacity of machine one between 2.67 hours and 16 hours, the rate of change of $14 an hour will not change. If you go outside this machine capacity, meaning that you change the right-hand side of the constraint outside these bounds, that will produce a different dual price or a different shadow price. It's no longer going to be $14 an hour. It's going to be something else. Okay, so as long as we keep the increasing or decreasing the capacity of machine one between 2.67 hours and $60 an hour, the rate of change will not change. is going to be $14 an hour.
In this, the original, eight, I mean, by $14 now, right? By
Yes. So what this is saying is, if you're gonna make $128 here, and you increase by 1 hour, that increase. You don't have to solve this again. You know that by increasing by 1 hour, this is gonna go $14 more. If you increase by 2 hours, that's gonna go to 128. If you increase, I'm sorry, if you're gonna go 28 extra dollars. As you increase one unit of resource, you know that your price or your profit is gonna be increasing by $14 an hour. If you move on the opposite direction, it's gonna be it's gonna be less than. Okay, so you're gonna be subtracting. So if you go from 8 to 7, now you're subtracting $14 out of your profit. If you go from 8 to 6, now you're decreasing that by $28. If you go, so it will change according to your original solution. Your original solution is here. You move in this direction. You're going to be increasing your profit by $1. An extra hour is going to add you $14. 1 hour less will decrease your profit by $14. Okay, and that's going to hold as long as you're within this bounds. If you go outside those bounds, then your problem basically is changing, or the solution of the problem will change. So yes.
So low price is the amount of money that our profit change.
Yes, is the rate of change according to your changes on the right-hand side, which is what we are looking at right now for one of the machines. Now, if we look at both of them at the same time, then you know the rate of change is going to be influenced by both of the changes of the machines. So right now we're just focusing on one of the machines. Using similar computations, you can verify that dual price for machine 2 capacity is $2 an hour. So if we just focus on machine 2, okay, so machine 2 is this constraint right here. For this rate wet constraint, if we go through the same process that we did for machine 1, instead of $14 an hour in terms of profit that you're going to increase, the rate of change or the shadow price or the dual price for machine 2 is going to be $2 instead of 14. So you're not making that much when compared to machine 1. So using the similar computations, you can verify the dual price for machine 2 capacity is $2 an hour. And that will remain valid for changes in machine 2 capacity within the line segment DE. So DE will be this line right here, or basically the constraint for machine 1. So as long as you move that line between D and E, you move this red line between D and E, that rate of change is not going to change. Yes.
So when you're looking at like the two and
yes,
you look at the other
you
that like intersect the x-y-axis.
You look at the points associated with that other constraint. That's right. So you're looking at the bounds basically for that other constraint. This constraint will go from this point to this point. So that line will be changing from that point, or will run parallel from top to bottom using that line as a reference. That's right. So if we go back to computing machine 2 capacities at point D and E, we can find that the minimum machine 2 capacity using constraint x1 plus 3x2, machine 2, that would be 1 times 4 plus 3 times 0. That is 4 hours. And then this should be, I'm sorry, this should be 0 and 8. This will be 1 times 0 plus 3 times 8. So this is 24 hours. So the conclusion is that the dual price of $2 an hour remains valid within this range. So as long as you keep the capacity of machine 2 within 4 hours and 24 hours, your rate of change is going to remain $2 an hour. Okay, so for this simple example, again, you're looking at a problem, production planning problem, in which you have a limited resource. In this case, the time that you have for machine 1 and machine 2, and you have a product or you have 2 products with different requirements for the use of those machines. So we're solving this problem using the graphical method. We can find the optimal solution with the given constraints. So we found that solution, and the profit that we found for the solution of this problem, let's go back all the way to here. Here, this is the optimal solution, 128. Obviously, we know these are fractional numbers, so we're going to address that later on. But for now, let's assume that this is the solution, fractional numbers. This is 128 in terms of profit. The question that we are asking now is, if it's a good decision for me in terms of profit to increase the capacity of my resources. So basically, what I'm saying is, what will happen if I increase my capacity of machine 1 from 8 hours to 9 hours? Would that be a good decision? Same thing for machine 2. If I decide to increase the capacity of machine 2 by 1 hour, is that a good decision or not? So what we are doing here is we're doing a sensitivity analysis. We're looking at what will be the impact of changing that resource, in this case, adding a resource an extra hour. And we saw the problem for one of those cases. For machine 1, we increased that resource by 1 hour, and we solved the problem again. And we found that the optimal solution increased by just increasing machine 1 by 1 hour from 128 to 142 dollars. So what that means is we have a rate of change associated with increasing the capacity of machine 1 or constraint 1. And we found what was that rate of change using this equation. So it's basically that we're computing the slope here, basically in terms of changes. So C is the objective function for this point G, which is the new optimal solution. And we're subtracting the objective function value for C, which was the original objective function. And we are also computing the capacity change, which was 1 hour. And that rate of change is $14 an hour. So what we have found here is, this is how much of a profit you're going to increase every time you add an hour of resource for machine 1. Okay, and we did the same thing for, and we call that the dual or the chattel price. That rate of change is called the dual and or the chattel price. And we also found the bounds for those when that is going to apply. Okay, so as long as you are between these 2 points, that line is going to be moving from point B to point F without issues. That optimal solution is not going to change. It's going to stay this point, or if you move to this point here, let's say you add 2 hours, then the optimal solution is going to be moving here. So that's why it doesn't matter where you move that line, the optimal solution will always move with that line. If you move it here, it's not going to change. If you move it here, it's not going to change. If you move it here, that optimal solution will always be associated with that intersection. So as long as you are between those 2 points, the optimal solution will move with the constraint. So that's why we are saying, okay, we need to find those bounds where this rate of change is going to be feasible. It will always be between this point. Why is not, if we move it to this point right here, that's no longer applies because the optimal solution is now changing. It is associated with a different constraint, right? So machine 1, or actually machine 2, is no longer a constraint that is impacting that solution. Okay, because now the optimal solution will move to this intersection where this x2 greater or equal to 0 is, and that optimal solution will be here. So that's why we need to find the bounds, because we know that the optimal solution, as long as you are between these 2 points, is not going to change. It's always going to be the intersection of those 2 constraints. We did the same thing for machine 2, and we found that the dual price for machine 2 will be $2. Sorry. And we also did the same exercise. We found the bounds. As long as you are between those 2 points, the objective function is going to be moving with those 2 constraints. So now that we know the computer limits for machine 1 and 2 are referred as the feasibility ranges. Okay, so that's what we call them. Software packages provide information about the dual prices and their feasibility ranges. So we will see that later on with Excel, maybe on Wednesday. The dual prices allow making economic decisions, about the LP problem, as the following questions will demonstrate. Okay, so let's try to answer these questions with the information that we have about this problem. So question 1, if job code increase or can increase the capacity of both machines, which machine should receive priority? So that's a question for you. If you had to make a decision of increasing one of the 2, which one would you go for? The first one, right? And the answer is easy, right? You have an increase of profit of $14 versus an increase of profit of just $2. So each additional hour of machine 1 increases revenue by $14 as opposed to only $2 for machine 2. Those are based on the dual prices. So the priority should be given to machine 1. Question 2, a suggestion is made to increase the capacities of machine 1 and 2 at the additional cost of $10 an hour for each machine. Is this something that you would advise? Well, you have to look at this machine individually. So it's an additional cost of $10 for each machine, right? So if based on our analysis, we can look at machine 1, right? Machine 1 is giving you $14. So if you add additional cost of 10, you're still making $4. But that's not the case for machine 2, right? Machine 2, if you increase the an hour of resource, just giving you an extra $2, and you're going to spend $10 for increasing that capacity, that's not advisable. So for machine 1, the additional net revenue will be $14 minus 10. For machine 2, the additional net revenue per hour will be only minus 8. So you're going to be spending more money. So only machine 1 should be considered for a capacity increase. So that's I would say these are the most practical concepts that you will get from this course, because it's not only solving the problem, it's also looking at different scenarios and making decisions in terms of what will be better for your process, like in a practical setting. Like if you're looking at production scheduling, if you're looking at production for your products, you have this solution and you want to see, can I do better? Okay, you have the optimal solution for the scenario that you have in front of you, but you can also go an extra mile and say, okay, what if we do this change in the company? Can we make more money, or can we improve our process, or can we increase our revenue? And that's what the sensitivity analysis will allow you to do. Question 3, if the capacity of machine 1 is increased from 8 hours to 13 hours, how will this increase impact the optimal revenue? So now we are adding 5 hours to our machine capacity. So dual price for machine 1 is $14 and is applicable to the range 2.67 and 16 hours. So first of all, we need to make sure that recommended increases within the bounds that we define, right? And the answer is yes. 13 is within these bounds. So that's something that we can do. We know that the optimal solution will not change as long as that point is moving between 2.67 and 16 hours. So that's a change that we can do. So the 13 hours falls within the feasibility range. Hence, the increase of revenue is $14 times the difference, which is 5 hours. So that will increase your profit by $70, which means that the total revenue will increase from $128 to $198. Okay, so yes. The optimal revenue and the total revenue. So I guess the optimal solution will give you the total revenue for this problem. Total revenue doesn't necessarily connect or yeah. Optimal revenue is basically, this is going to be the best scenario for your solution, or this is going to be the best you can do in terms of profit given the constraints for your problem. Total revenue doesn't necessarily mean that it's the optimal. Okay, when you say optimal revenue is the best you can do. Okay. So question 4, suppose that the capacity of machine 1 is increased to 20 hours. How would this increase affect the optimal revenue? Proposed change is outside the feasibility range. Okay, so that's why I want you to be aware of that feasibility range, because if you go outside, then this dual price will not hold. Okay, so if you go outside this feasibility range, for machine 1, that will be 2.67 and 16 hours. If you go outside that range, then we're going to have to solve the problem again. Okay, because the solution is going outside the constraints that we identify for our optimal solution. So in this case, further calculations are needed to find the answer. And that's what we're going to cover on our next lecture using the dual models. Okay, that makes sense? What that means in terms of, again, as I explained, you will no longer have your constraints moving in the same intersection. So you'll be outside that constraint. And for that, you're going to have to solve the problem again. Okay, so now we're going to look at the second case. So we were focusing on the right-hand side of the constraints. Now we want to perform graphical sensitivity analysis on the changes in the coefficients of the objective function. Okay, so changes in revenue or the objective function coefficients will change the slope of the objective function we call C. However, the optimal solution at point Z remains unchanged as long as the objective function lies between lines BF and D. Okay, so in this representation, we are illustrating the isoprofit or the objective function line. Okay, so you will see that that objective function is in between the constraints that are defining our optimal solution. which are the constraints for machine 1 and machine 2. So you see that objective function is in between those two constraints. Okay, so this is constraint 1, this is constraint 2. So the constraints, and you can see that the objective function is in between those two constraints. Okay, so what we want to see, if you remember our explanation of the graphical method, as long as that slope is constant, you move up and down, doesn't matter, your optimal solution will be identified by the objective function. And that optimal solution is not going to change as long as that slope is in between those two constraints. Because if you move those lines, in this case from left to right, it doesn't matter that slope. As long as the slope is between those two constraints, the objective function value is going to be the same. However, if you go outside those two, that slope is going to lead you to identify a different point in the feasible region. Okay, so the optimal solution at point C will remain unchanged as long as the objective function or the slope of that objective function remains between these two constraints. If you go something like this, let me illustrate that. Let's say the slope is now something like this, right? Now, if you move that line up and down, the optimal solution will be this point. It's not going to be this point anymore. Because you identify the optimal solution as the last point that is touched by the isotropic line in the feasible region. So if you move this in this direction, that will be this point. And that will happen with every point for a slope that is not inside these two constraints. If you, for example, you move this one up and down, you know, even though the slope has changed, you will always identify point C if you move that constraint up and down. You move this one up and down, that point is no longer going to be identified as the optimal solution. That will be this one. So that's why for the sensitivity analysis of the objective function, we have to be aware that we can make changes to the objective function coefficients. We can apply the sensitivity analysis, and as long as we don't go outside these bounds. Okay, so that's what we are going to identify now. So how can we determine the range for the coefficients of the objective function that will keep the optimal solution unchanged at point C? Okay, so first we write the objective function in general form. Okay, so that will be maximize Z equals C1 X1 plus C2 X2. So C1 and C2 are representing coefficients. This could be any number, 5, 12, is a number. Okay, so I'm representing the number with a coefficient C1 and C2. Imagine now that the line is pivot at C, which is point C, and it can rotate clockwise and counterclockwise. The optimal solution will remain at point C so long as this function, Z equals C1 times X1 plus Z2 X2, lies between the two lines X1 plus 3X2 equals 8 and 2X1 plus X2 equals 8. This means that the ratio C1 over C2 can vary between 1/3 and 2/1, which yields the following optimality range. So how do we find those ratios? Those are the coefficients. So this will be 1, this is 3, this is 2, and this is 1. So the coefficients associated with the first constraint are 1/3. The coefficients associated with the second constraint are 2/1. So that will tell us the following. As long as these coefficients for the objective function are between these two or 0.333 less than or equal to C1 over C2 less than or equal to 2. This means that the ratio C1, C2 can vary between 1/3 and 2:1, which yields the following optimality range. In this case, that'll be 1/3 over 1/3 less than or equal to C1 over C2 less than or equal to over 1, or 0.33 less than or equal to C1 over C2 less than or equal to 2. Okay, so let's look at some applications of these ideas. So suppose that the unit revenues for product 1 and 2 are changed to 35 and 25 respectively, with the current optimal solution remain the same. So what we need to do is to find out whether or not that ratio is within the bounds. The solution at C remain optimal because C1 over C2 equals 1.4. Will remains within the optimal range. The optimal value of change to 35 times 3.2 plus 25 times 0.6, which is going to be 152. Okay, so let's go back to this. So we want to know whether or not if we make changes to the profit that we are making, if we increase or decrease those by product, if we are going to remain, or if our optimal solution will remain the same. How do we find out if that's correct or not? We have to compute these bounds, which are the ones telling us whether or not these will remain the optimal solution. And those are going to be based on the coefficients that you are inputting into the objective function. Okay, so C1 over C2 has to be greater or equal to 1/3 and less than or equal to 2/1. Those are coming from the coefficients of the constraints. So for the first case, yes, this is less than 2, greater than 0.33. So that those coefficients will remain optimal. So if we increase the profit, yes, we're going to still make, we can still have the same optimal solution. We're going to make the same number of units, but we're going to increase our profit from 128 to 152. Suppose that the unit revenue of product 2 is fixed. Yes, go ahead.
So if we get the revenue, the product 1, not to 35, but let's say to 55, so it'll be out of the.
Yes, it will be outside the feasibility range. Yes, but if obviously you continuously increase the revenue that you're making by selling products, your profit is going to increase, right? But the problem is we have a limited number of resources, right? And we have a requirement for each product in terms of using those resources. And that's, that's creating our visibility, our visible region. And based on that, we are making, actually based on the original coefficients for the cost and the revenue, we are making the optimal solution given the resources that we have available. Okay, so your question is, if we increase the profit, obviously we're going to be making more money. That's correct. The problem is, if you want to make sure that your solution is not changing, meaning that you are going to be making the same number of units, in this case 3.2 and 1.6. If you want to remain in this point, which is your optimal solution, you only have certain coefficients that you can use to remain here. If you go above 2, you're basically no longer, your solution is no longer staying here. The solution will move to another plane in this physical region. And what we are trying to say is not that that's incorrect. What we're trying to say is, if you want to find the best coefficients and still produce the same number of units, this is the feasibility range. We want to find the best coefficients for this optimal solution. If you go outside this feasibility range, you're going to find a different solution, no longer this one, and you're going to have to solve the problem again. Okay? So the analysis that we are trying to make is based on the solution that we have on hand. We have the original problem, we solved the problem, we found the optimal solution. Now we are trying to say, okay, can we do better based on this solution that we have on hand? How can we increase our, let's say, can we increase the prices and with the solution that we have so far, do better without changing the solution that we have on hand?
So on the solution.
So what that means is, if you go outside this, range, 0.33 and 2, you have to solve the problem again. You're looking at the sensitivity analysis of the solution that you have on hand. And those feasibility ranges are telling you you can do changes to the coefficients as long as you are between these bounds. If you go outside those bounds, then you have to solve the problem again, because the solution that you're going to obtain is no longer here. It's going to be somewhere else. You have to put those coefficients, new coefficients, into the objective function and solve it using the simplex method. Okay? So the analysis that we are presenting in terms of sensitivity analysis are based on the solution that we found for the original problem. So the questions that we are trying to answer is, okay, this is my optimal solution based on the limitations and the numbers that I have right now. Based on this optimal solution, can I make changes to the coefficients and do better, but keeping the same solution? Okay.
So sensitivity analysis based on the conditions, number of
is under the condition that we are keeping the same solution. The solution is not going to change. The solution is going to be always between the intersection of these two constraints. If you go outside those bounds, the solution is not going to be in the intersection of these two constraints any longer. It's going to be somewhere else. Okay, so we are basically basing this analysis on the solution that we have found, the optimal solution that we found for the original problem. That solution is not going to change as long as it's always going to be between the intersection of these two constraints as long as we keep the numbers inside the feasibility range. If you go outside those feasibility range, it doesn't mean that the solution is incorrect. What it means is that you have to solve the problem. You might find a better solution, but the solution is going to be found in a different location. It's not going to be here anymore. Okay. Or you might find out that the solution is infeasible, or yeah, but we're going to have to solve the problem again. Okay. So the solution, and that's what we're saying, solution as C will remain optimal. Okay, so we know that if we increase the values for the profit to 35 and 25, we still keep the same original solution, optimal solution, but the profit is going to be increased because we are increasing the numbers, the profit. So from a practical point of view, if you go, for example, if you make this 50, see, we're saying this 150, that will be greater than 2, right? So what that is saying is, if you solve this problem, what I'm trying to see is, if you make this 50, what this is going to say is, I'm going to make more units than 2 than 1, right? Because I'm going to be able to make more profit. Right now, my solution is telling me I do more X1 than X2, but if you go outside that range, you might go to making more units of 2 than 1, right? So right now you're making 3.2 x1, x2 equals 1.6. But if you make x2 more profitable by increasing the profit of x2, then you are going to be making more x2 than x1. So that solution is changing. So let's go back to so as long as you are in these bounds, your solution is not going to change. Optimal solution is not going to change, but your profit will be increased because you are increasing the coefficients. Changing those coefficients between these bounds will allow you to keep the same optimal solution. Then we have question 2. Suppose that the unit revenue of product 2 is fixed and its current value, C2 equals 20. What is the associated optimality range for the unit revenue for product 1, C1, that will keep the optimal unchanged? So now what we want to do, okay, what we are saying is, let's say we know that this is not going to change. How much can I increase the cost, the profits of C1 so I stay in the feasibility range? Okay, so what we are doing is basically substituting C2 into this equation. So we're going to make this equal to 20. And we're going to end up with 1/3 times 20 less than or equal to C1. And then 2 times 20 less than or equal to 40. So this is 6.67 less than or equal to C1 less than or equal to 40. Okay, so the most that I can increase the profit of my product 1 is 40, so I can keep the same optimal solution. If I go above 40, then the solution would change. The optimal solution would change. What that means is if I make it 41, I might end up producing only X1s. So X2 is not going to be any longer part of my production schedule. So that's why I need to resolve or solve the problem again. As long as I keep it within 40, I know that I'm going to still produce some units for X2. If I go above that, I might kill product 2. I mean, if I'm selling very well and I'm increasing my prices, right? I might stop doing product 2, will go only to product 1. And that will happen if you go above 40. On the other side, if you go below 6.67, then you might go straight to producing only product 2 and not produce product 1. And so this is what these coefficients are trying to represent. Yes.
So that $20 from closing or like who's going to decide whether it's
This is given here in this statement. So we suppose that the revenue of product 2 is going to be fixed at 20. It's not going to change. Okay, so that's given in the statement. Suppose
the
that
whole thing I was asking a question, like I just couldn't understand if you put a question from this part, how it will be planned.
so if I were to put a question like this, like for example in the exam, yeah, I can give you a report, a sensitivity analysis report. I can ask you questions about that sensitivity analysis, questions like this one. So you should be able to, and we're going to go through the reports in our next lecture. And then based on that report, I'm going to be asking you questions like this one. So you have the dual price for each, you have the shadow price, dual prices for each one of your coefficients. You have the values in terms of the coefficient of the objective function. And based on that, I can set up some scenarios and you should be able to tell me, yeah, this is good, this is not good. I will do this, I will not do that. Yeah. Any other questions? It looks like I'm gonna stop here. I don't want to start with the algebraic sensitivity analysis. So we're going to start with the algebraic sensitivity analysis on Wednesday. And as I mentioned at the beginning of the lecture, I'm gonna also provide feedback on the second exam on Wednesday. Any questions? Good. So I will post a video and the notes for today's lecture later today, and then we'll continue our discussion on Wednesday.